Acti, the impossible star. Every single morning, you step outside, look up at the sky, and feel the warm light of the sun on your skin. We take this bright, glowing ball of plasma for granted. It has been shining steadily for 4.6 billion years, providing the energy required for every plant to grow, every ocean to flow, and every human heart to beat. We are taught in school that the sun is a giant nuclear furnace. Deep inside its core, immense gravity squeezes hydrogen atoms together, fusing them into helium and releasing massive bursts of energy in the process. There is only one problem with this story. According to the fundamental laws of classical physics, the sun should not be burning at all. In fact, mathematically speaking, the core of the sun is far too cold to ignite nuclear fusion. By all traditional laws of nature, our star should have remained a dark, cold cloud of gas, and our solar system should be a frozen wasteland. This is not a scene from science fiction or a flaw in our measurement instruments. This is a real paradox that stumped the greatest minds in physics for decades. The sun is only alive today because of a bizarre, microscopic glitch in the fabric of space, a quantum phenomenon where subatomic particles cheat reality by walking directly through solid walls. Hi friends, welcome to a new video from Science Simplified for All. Today, we will explore the mind-bending physics of quantum tunneling and discover why we owe our very existence to an impossible subatomic escape trick. Act 2, the electromagnetic barrier. To understand why the sun shouldn't be burning, we must first look at what it actually takes to fuse two atoms together. At the center of a hydrogen atom sits a single positively charged particle, a proton. To create nuclear fusion, the core of the sun must force two individual protons to collide and bind together to form deuterium, the first step toward creating helium. However, nature has built a massive defense mechanism against this process. You have likely played with magnets before. If you try to push the positive poles of two strong magnets together, you will feel a powerful invisible force pushing them apart. The closer you bring them, the harder they resist. Protons experience the exact same phenomenon on an atomic scale, known as the Coulomb barrier. Because both protons carry a positive electrical charge, they repel each other with incredible force. The closer to protons get, the stronger this electrical repulsion becomes. The only way to overcome this repulsive force is to smash the protons together at breathtaking speeds. If they get close enough, specifically within 1 femtometer of each other, a different force takes over, the strong nuclear force. This force acts like powerful atomic glue, binding the protons together and releasing a tremendous burst of thermonuclear energy. To slam protons together with enough velocity to break through the Coulomb barrier, you need extreme heat and pressure. Physicists calculated that to ignite hydrogen fusion through sheer mechanical force, the temperature at the center of a star must reach roughly 3 billion degrees Celsius, and that is where the math completely breaks down. Act 3, the cold core paradox. When scientists measured the temperature at the core of our sun, they found it is only about 15 million degrees Celsius. While 15 million degrees sounds extraordinarily hot to us, in the language of nuclear physics, it is a freezing cold drizzle. At 15 million degrees, the average proton in the sun's core is moving far too slowly. It possesses less than 1% of the kinetic energy required to overcome the electrostatic repulsion of its neighbor. Imagine trying to throw a baseball over a 100-meter-tall concrete wall. If you only have the strength to throw the ball 2 meters into the air, no matter how many times you try, that ball is going to bounce off the wall and fall back to the ground. It will never cross over to the other side. In classical physics, the electrostatic wall around a proton is simply too high. When two slow-moving protons hurtle toward each other in the sun, the electrical repulsion acts like that 100-meter wall. The protons should bounce off each other long before they ever touch, making fusion completely impossible. If classical physics ruled the cosmos, the sun would have collapsed billions of years ago. So how does the sun produce light? The answer lay hidden in a revolutionary idea proposed by a young physicist named George Gamow in 1928. The protons don't throw themselves over the wall. They walk straight through it. Act 4. The proton that walked through walls. In our everyday macroscopic world, objects are solid, rigid, and predictable. If you throw a tennis ball at a brick wall, it will bounce back every single time. It doesn't matter if you throw it 1,000 times or 1,000,000,000 times. The ball remains on your side of the wall, but as we have explored in previous videos, The quantum world operates under a completely different set of rules. At the subatomic scale, a particle like a proton does not exist as a solid, localized marble. Instead, according to the laws of quantum mechanics, a proton is described by a wave function, a spread-out cloud of probabilities mathematically, defining where the particle might be located. Because a proton is a fuzzy wave of probability, rather than a hard sphere, its presence is not strictly confined to one exact point in space. When a proton approaches the formidable electrostatic wall of another proton, its probability wave doesn't just hit the barrier and stop dead. Instead, a tiny fraction of that probability wave bleeds right through the barrier and leaks out onto the other side. This means there is a small, non-zero chance that the proton will spontaneously disappear from one side of the electrical barrier and instantaneously reappear on the inside, bypassing the wall entirely, without ever having enough energy to climb over it. This phenomenon is known as quantum tunneling. The particle hasn't smashed through the wall or broken it. It has simply used its wave-like nature to teleport across a barrier that should have been physically impassable. Act V, a 1 in a septillion chance at this point. You might wonder, if quantum tunneling is real, why don't humans accidentally walk through solid concrete walls? The reason comes down to scale and probability. The odds of a single proton tunneling through another proton's Coulomb barrier in the Sun are staggeringly small, roughly 1 in 10 to the power of 28. That is a 1 followed by 28 zeros. To put that into perspective, your odds of winning the lottery every week for an entire lifetime are dramatically higher than the odds of a single proton tunneling through a barrier on any given collision. If the Sun only contained a few thousand protons, quantum tunneling would be far too rare to matter, and the star would stay cold and dark. But the Sun is unimaginably massive. The core of the Sun contains a staggering number of protons, roughly 10 to the power of 56 particles, all jammed into a super-dense plasma state, colliding trillions of times every single second. When you multiply an impossibly tiny quantum probability by a gigantic astronomical number of particles, the impossible becomes an absolute certainty. Out of the endless septillions of failed collisions happening every second, a tiny fraction of protons successfully tunnel through the barrier, fuse together, and ignite the nuclear reaction. It is this slow, steady drip of quantum tunneling that acts as the Sun's thermostat, allowing it to burn quietly and continuously over billions of years rather than exploding like a giant hydrogen bomb all at once. Act VI, the quantum engine of reality without quantum tunneling. The universe as we know it could not exist if the Sun burned through pure classical mechanics. It would have consumed its fuel in a violent flash or never ignited at all. Because of this microscopic quantum glitch, stars can shine for billions of years, giving life enough time to evolve on orbiting planets like Earth. Every photon of sunlight hitting your face today, every ray of light nourishing a forest, and every calorie of energy powering human civilization is a direct result of a subatomic particle performing an impossible ghost trick in the center of our local star. Today, engineers are even utilizing quantum tunneling to build modern technology. The flash memory inside your smartphone, solid-state drives, SSDs, and scanning tunneling microscopes all rely on electrons tunneling through physical barriers to store data and image individual atoms. The next time you look up at the Sun, remember, reality is not a solid, rigid structure. Beneath the surface of everything we see, subatomic particles are constantly breaking the rules of classical physics, cheating barriers, and shaping the universe one impossible quantum step at a time. Thank you for watching. If you found this breakdown of solar physics fascinating, hit the like button and share it with your friends. Don't forget to subscribe to Science Simplified for more clear explanations of the universe's greatest mysteries.